So key ideas from CENG 100 that we're going to work with. We're going to start with batch reactors. We're going to spend, as you saw on the syllabus on Monday, we spend about 3 to 4 weeks on batch reactors, which has the advantage of making the material balances really, really easy. There's not very many terms because there's no flow parameters coming in or out. It also makes the energy balances really, really easy. Well, it's dangerous to say something is really, really easy. It's a lot simpler than the flow problems that we'll get to afterwards. So if you remember from a batch reactor was the simplest thing that we could come up with. It was basically a bucket. And we would put stuff in the bucket, and then we would wait a while, some amount of time t, and then we would come back to the bucket afterwards, and we would have some new set of species inside there, right? The world's best batch reactor up there. And generally, we depicted that as an initial state over here and a final state over here. As we went along, if we wanted to calculate the moles of something that was in there, we generally define the moles as capital N sub whatever the component is. And that component in the initial state was denoted with a little 0 underneath it. So maybe there was some A, some B, and some C in there. So we would have NA0, NB0, NC0, as much as you want. It doesn't particularly matter at this point because we haven't come up with anything beyond the generics. And then at some time t after you're done, or if you just were interested in it after a particular time, the amount of moles remaining were Na or Nb or N whatever it is that we have, without the little subscript 0. And so the general reaction that we're talking about here, we would write it as a stoichiometric coefficient lowercase a plus lowercase b times species b is going to a lowercase c, capital C for species C, and d times d. All right, that was about the simplest generic reaction that we could come up with. We probably modified it a little bit in CENG 100 for things like reversible reactions, and we'll get to those eventually. The way that we solved these sorts of problems in CENG or CENG 100 was usually to create what was called a stoichiometric table. And we do the same thing in this class, but we are going to modify the definitions a little bit because we're going to introduce some parameters that initially make it look like, well, why did we do that? We had a perfectly good way to do it in 100. You just made it more complicated. But those parameters show up again and again in both the material and the energy balances. So it's easy in the long run to introduce these parameters now, even though it looks like it's a little bit more clunky than what we had seen before. So the way we had done stoichiometric tables before, the minimum number of columns that we had were columns for species, some amount of whatever species I is initial, and some amount of species I final. You might have had a column for, is the mic too loud in the back? Is it like screeching? I love the sound of my own voice, but I know it can be too loud if the mic is up. You're good? Okay. So that you could have had additional columns in the stoichiometric table, like sometimes there was a new column that came after species. You probably had a delta column somewhere in between the initial and the final. But the general approach was we would do something like list each one of our species, A, B through whatever, followed by however much we started with, like Na0, Nb0. You know, for the products, they were probably 0 because we didn't start with anything. And then we had one way to calculate everything that was coming out, which was N sub A was always equal to however much you started with, which is Na0, plus the stoichiometric coefficient for A times the odd-looking squiggle, which I believe the proper pronunciation in Greek is xi. And if you had me for 100, you know I just call it squiggle. That was the extent of reaction that we had. And this extent of reaction parameter was useful because it's the same extent of reaction for all of those species. So if we want to know what's happening to species B, we would write N sub B is equal to N sub B0 plus the stoichiometric coefficient of B times squiggle. I'm putting a subscript A on all those squiggles. If there's only one reaction, you don't need a subscript. But you may recall from CENG 100, if you have more than one reaction, there's more than one squiggle. I'm just saying subscript A to keep it in mind that it's with respect to this particular reaction up top. And that's the way that we did things in CENG 100. We're going to do about the same thing for 113, except we're going to introduce 3 parameters that make this table look a little bit different. But the entire concept is the same, right? When we get to this step over here, that's just a material balance, right? It says, let's see how close I can get. It says that you're left. Let's do this instead. All of these are saying is that whatever you're left with here in the green is whatever you started with in the red, plus whatever got changed by the blue. All right, that blue term is how much it changed, the red term is how much you started with, and green term is how much you got left. There's not a lot of deep science behind that. It's just counting up what's there and figuring out how much changed. We're going to do the same thing. Here are the 3 variations that we have. The first variation is to set the stoichiometric coefficient A equal to 1. When I say set it equal to that, you can have it, I can give you an equation where the initial coefficient is something other than 1, so 4A goes to something like 2C. For convenience, we're just, before you even get started on the problem, just rearrange that equation so that the stoichiometric coefficient on A is 1. So this would become A, divide everything by 4, and you end up with 1/2 C. That's just for convenience because it makes the math a little bit easier. All of this procedure works whether or not the stoichiometric coefficient for A is 1 or not, but you'll see the math looks a little bit nicer if you don't have to keep carrying around all those numbers. So that's almost something that you can do in your head. It's not particularly difficult. The other point for the stoichiometric coefficients that I wanted to remember was what? Oh yeah, they're positive for what and negative for what? Negative for positive for products, negative for reactants. So don't forget which way that goes. Next step, we're going to use the conversion x sub A instead of the squiggle. Why do we use conversion instead of squiggle? Normally, if you're working with a reactor, you are far more interested in how much of the product did I use up, rather than what is this obscure extent of reaction that I have. So the conversion x sub A has a nice physical interpretation because it always varies between 0 and 1, or 0 and 100%. And bigger is better, right? If I convert 100% of my reactant, I probably did a pretty good job. Otherwise, I wouldn't have been doing the reaction. So just for convenience, we're going to use x sub A instead of squiggle. Notice I did put another subscript on x sub A because it is always defined with respect to a specific component. We will always choose that component to be component A. How do you pick A? Any ideas?
Limiting reactant.
Could be the limiting reactant. That's a good one.
Any one of your choice.
Any one of your choice. How do you make a good choice?
I would take the one that's probably going to go away fastest. Or one
Well,
that's easy to keep track of.
Easiest to keep track of, that could be it. Expense could be another one. Maybe it's typically the one that is most expensive is also the one that is limiting so that you use it all up. But there is no cut and dry method for saying such and such a component is always A. You can't like crank the wheels through math or something and figure out what A is. You have to make a choice based on whatever the problem statement is to find out what A is. Most of the time it'll be pretty obvious, right? If there's one component that's degrading into two more, you only have one choice. It's only A. If it's something like combustion, it's probably the fuel that is more important because you're just pulling oxygen from the air or something like that. So the choice of A is up to you, but most of the time it should be fairly obvious which one is A and which one is not. That definition for conversion of A, it's still the same one we used in 100, but we tended to use it more as a process specification than something we would use to solve the problem. The definition of X sub A hasn't changed. The conversion of A is the moles of A reacted divided by the moles of A fed. Right, and so what that ends up looking like is Na0 minus N sub A divided by Na0. Right, not much change there. It's the same definition of conversion that we used before. A new definition that we didn't use in CENG 100, which I will put in red because it is new and it is easy to change colors, is a parameter called theta. It's actually a capital theta. A capital theta is very difficult to draw. A capital theta looks like a circle with an H inside, but it always ends up looking like a circle with an H inside, which might look like hydrogen. So I will generally draw this as a lowercase theta, which looks something like that. And it always has a subscript on it for a particular species I. And theta sub I, by the way, the reason I bring up the fact that it's a capital theta is because if you go look at Fogler or you look at your homework problems, you're going to see it typeset as a capital theta. It's the same thing. It's just difficult to draw. Theta is defined as the moles of any species initially present divided by the moles of A initially present. That's it. That's all theta is. So it's entirely dependent on how the system started. It has nothing to do with how the system finished. It's just saying if I take the ratio of whatever I started with to the ratio of what I started with A, that's theta. The reason that that becomes useful is more in the energy balance. This is one of those points where I mentioned earlier, it looks like we're over complicating things for no apparent reason, but it will become a little bit more clear as we go. So if we have these definitions and these conventions, the first two are just conventions because that's the way that we write things. The third one is a new definition that will make more sense as we go. The stoichiometric table will also look a little bit different. So if we want to write a stoichiometric table for chemical reactions in CENG 113, it usually looks like this. Start off with the same columns. We'll still give the species, the initial, and the final. The final always follows a very nice form. Always looks like N sub A0 times theta I plus nu sub I times X sub A. That is, if you're playing along and you wrote down those important equations that I put up at the beginning, that is one of those new equations that we have that is very useful to keep in mind. The nice thing about that is you can apply it like a hammer to every one of these problems and just hit every species with that hammer because it looks the same every single time. All you have to do is pick up a theta sub I, which is the ratio of what you started with to this amount of A you started with, and figure out what the stoichiometric coefficient is of that particular species, all of which is going to come from the reaction that you have. So again, if we have something like species A, I'm going to skip and go down to D, because you know what happens for B and C. B looks like A and D looks like C. The amount that you started with is N sub A0, or N sub D0. And if I tack in a little theta here, who just got frustrated with me because I didn't put it on there at first and you don't have enough space for theta now? Okay, at least a few of you. Do you know what else I can do? Oh, people hated this in fluids. I can take like a theta like that and move it over here. And then I realize nobody else can do that. So if I do that, I'm sorry. It's just super convenient. Anyway, the theta sub I, what's theta sub I for A? It's always going to be 1, right? There's never anything other than, it can't be anything other than 1. By definition, theta sub I will be 1 for species A. For D, there's not really anything we know at this point, right? I mean, presumably D exists. It could be 0, it could be whatever we want, but all we know for sure is that theta D is theta D, right? However much D we started with divided by however much A we started with. Could be 0 or some other number. As we saw in 100, usually we don't start off with a lot of product, but it's not impossible. If I want to know how much A I finish up with, N sub A All I have to do is follow that pattern. NA naught, theta is always going to be 1. By convention for this class, we always set the stoichiometric coefficient for species A, whichever one is important, to be 1, so this will always look like 1 minus x. Right? The first line in your stoich table always looks like however much you started with times 1 minus x. Then it becomes pretty straightforward to write the rest of these because they all look very similar. N sub A naught times however much you started with, so this is theta sub d. Usually the d, assuming it is a product, is going to be negative, so it would be minus little d for the stoichiometric coefficient of d times x. Right, and this should look pretty similar. If there was no d initially present, then n sub d is just equal to, what's theta if there was no d initially present? 0, right? Nothing happened. Or, sorry, not nothing happened. Nothing was originally there, so it's NA naught times minus d times x. Keep in mind that is stoichiometric coefficient d, not derivative d. There are going to be derivative d's in a moment. And then the last ones that we usually get, or we sometimes get, is when we're all done, we sum things up, just to figure out how much we have total. So the initial number of moles total was simply the sum of all the stuff that we started with. That is supposed to be a capital sigma that represents summing everything up. Who's not seen a capital sigma before? Okay, because we're going to use, who's seen capital pi for a product? Okay, most of you have seen capital pi. Yeah, question?
Why d is negative?
Because, oh no, you're right, sorry. Please, if you see stupid mistakes. I mean, don't call me stupid, but at least point them out so that I fix them. Yes, we should always be producing product D. Right, and then if we also want to know what's happening with the total number of moles coming out, which I'm skipping the algebra here. It's however much we started with times something to do with however much changed. You can go through and prove to yourself how this ends up working. It's generally the stoichiometric coefficient of D and the stoichiometric coefficient of A minus B over A minus 1. So that can look a little bit odd. The reason that that looks a little bit odd is because I am explicitly including that calculation that you probably did in your head that set A is equal to 1. This would look, if A was not 1, that would look the same except it would say D plus C minus B minus A. But because as a convention in this class we usually set A equal to 1, we write it like this just to make it clear to everybody that A really is there. That 1 is not anything special out at the end. That's just what we set A to be. So all that is the difference in the stoichiometric coefficients times NA naught times X. Right, and you will get this equation. I'm not going to walk over there and disconnect myself again. You will get this equation if you simply sum up all of those terms. That is exactly what this is down here. There's no magic to what happened there. We just summed them up and did some algebra to make it look a little bit simpler. One parameter that we introduced that you've probably not seen before, which again is more useful when you're talking about gases and energy balances, this parameter has a special name, and we call that delta. It doesn't have a name, like X has a name called conversion, right? And conversion is represented by the symbol X. That sum of the differences between stoichiometric coefficients doesn't really have a name, but it's always given the symbol delta, which just makes the equations a little bit more compact to write. So in general, the equation that's of interest whenever you're writing a stoichiometric table is this one. Right? The rest of the table came from initial conditions. Everything over on from the first column, second column, third column, those are all however the system started. You don't have to do too much thinking to figure out how the system started. If you want to know how the system finishes, then it's over here in the far right column, and you can write down every one of those very, very quickly by simply applying that formula every time. And that's not anything different than we saw in 100. Again, it's just using a slightly different notation to say exactly the same thing. What happens if you have an inert in your system? How does that get included in the stoichiometric table? You get another row. You'd have to write another row, but what's different? There's no change. The stoichiometric coefficient on an inert is 0, right? It doesn't participate in the reaction. So if you do have an inert sitting inside the system, which is usually given by capital I, now you have n sub I 0, and the amount of inert you end up with afterwards, if the stoichiometric coefficient is 0, then you will simply have Na naught times theta sub I, where I is for the inert, which is just n sub I naught. Right? By definition, the inerts don't participate. The reason that inerts are important is because they will show up in the totals. Right? And that'll be particularly important if you start dealing with concentrations, because even though the amount of n sub I, the inert, doesn't change, its concentration can change. And we'll see why that happens in a moment. Any questions on that part? Okay. A variation on the stoichiometric table that we make, because concentration tends to be a more useful parameter than total mole. The reason it becomes more useful is because when we start talking about rates, rates are always defined in terms of concentration. They're proportional to concentrations. So concentration has a very specific definition. So the concentration of any species I is equal to the moles of that species I divided by the volume of the container that's holding those species. So sometimes we use the word concentration a little loosely to mean like mass fraction or mole fraction or something else. This is the way concentration will always be used in this class. It always means the amount of stuff you have, or the moles, divided by the volume of the stuff that you're working with. In a batch reactor, V is usually fixed. And so it doesn't matter if you're talking about the initial volume or the final volume, it's the same thing. So V sub 0 is the initial volume. Batch reactors usually have a fixed volume because you just dump stuff into a steel container and seal it. Right? You can't make that container any bigger or smaller unless you're trying to do like those thermo problems where you have like movable frictionless cylinders or something like that. And then you have adjustable volume, but we don't deal with adjustable volume because they're math problems. They don't come up very often. So we do have an equation for n sub I. Right? The general form of n sub I is n sub A0 times theta sub I plus the stoichiometric coefficient times x divided by V sub naught. So as long as you're dealing with a constant volume batch system, this equation holds. And now we have this little term here, Na naught divided by V naught. That term is going to be equal to C sub A naught. Right? The definition of concentration is N over V. If we happen to have an Na naught over V naught, that's the concentration of A we initially started with. There's not much, that's the definition of C. That's how we do that. So another version of the stoichiometric table can be written entirely in terms of C. So you'd have a species column, the amount of C that you started, or not CA0, CI0, and then the amount of, the concentration you started with afterwards, which is always going to be equal to C sub A0 times theta I plus nu sub I times x. Very importantly, though, this is only for batch. Right? We will see a different equation for C sub I if we move to a flow system. This will actually always hold for a liquid, so I guess we can add that. Either batch or a liquid. Most reactions are not liquid phase that we deal with on a large scale. But that will hold exactly for a liquid, even if the volume is, well, the volume can't change for a liquid. That's why it holds. But it holds no matter the phase, whether it's gas or liquid, if you're in a batch system, because a batch system typically has constant volume. That's why we were allowed to make this simplification here, where we changed a V to a V naught. As we will see when we switch to gas phase flow systems, we can't say that V is equal to V naught, so we have an additional correction term to get in there. But for a batch system, we're good to go with something like this. And so this system doesn't look too terribly different from the last one. We still have whatever we started with for each one of these, and then however much we finish, C sub A is equal to CA naught times 1 minus X. Presumably you can write all of those down for the rest of them, and then C sub D is CA naught times whatever the theta sub D is. Typically that will be plus, see, I remembered this time, D sub X, or sorry, D times X. And we can still add things up because we haven't lost our mathematical ability to add things up. We can count the initial, we can figure out an initial concentration by just summing up all those concentrations, and then the final concentration, C sub T, is equal to however much we started with, plus delta times CA naught times X. So there's a little bit of algebra in there that I skipped over, but if you compare what I've got here to what I've got here, the process is the same. It's just now we're dealing with C's instead of N's. All right, so those are two equivalent stoichiometric tables that you can write, both of which are essentially the same thing that you were writing in 100, with the modification that we deal with x's instead of squiggles, and we deal with thetas, because as we'll see, eventually thetas are a little bit more helpful. Any questions on stoich tables? I suggest that for the first few homeworks, even if you don't think that you need a stoichiometric table, write it down. It's an easy place to get started with. It's you want to have those equations, particularly, what was it? This one in blue. That should be ingrained in your mind because that is essentially all the work that you have to do to create a stoichiometric table. The rest of it sort of comes from the definition of, okay, what goes in this column, what goes in this one, what goes in that one. With that single equation, you can complete the hardest entry of the stoich table, or with this equation, which I guess I will put in blue again, here. That's the equivalent for a batch system if we're talking about concentration. The reason we typically will write it in terms of concentration and not moles is because rates are dependent on concentration, not moles. All right, so that part should have been reviewed from whatever week 3 or something from 100. There was a portion of 100 that we got to that had time-dependent material balances. Batch reactors always have time-dependent material balances, unless you're talking about somebody telling you what's the composition after I get a particular concentrate or particular conversion, right? There's nothing in here that says how long did it take for me to get to that situation. It just tells me where I started and where I finished. Usually we're much more interested in a batch reactor in how long does it take to get there, right? Do I have to come back tomorrow or next week, or should I redesign the system because it takes too long? So when we're dealing with batch reactors, this is a very useful point to get started with, but it's usually not how we end up solving the problem unless it's on an exam or something and I say, tell me what the concentrations are for a 20% conversion of X. Then you can dump it into a stoich table and figure out what are the concentrations when I'm all done. More often we start for a batch reactor with a control volume approach. So stuff is sitting inside of a batch reactor, and if I draw a control volume around the stuff, right? I can write a material balance around that control volume. Remember, material balance is accumulation is in minus out plus generation minus consumption. We're going to lump the generation and consumption terms into a change term, right? At this point, we don't really care if things are increasing or decreasing. They're just changing. So if I wanted to write down how the moles of anything changes in this particular system, the rate of change of any moles of species I, dNI dt, is going to be equal to in minus out plus, I'll just call it delta to represent a change. But ever so conveniently, in a batch system, there is no in or out, right? So both of these go away, which is nice. That's one of the reasons why we're starting with batch, because it makes this system very easy. The delta term is always going to look like R sub I times V. So R is our reaction rate, V is the volume of whatever we're dealing with. We're going to learn more about the components of R tomorrow because it consists of a couple of different terms. The advantage to writing it, so first of all, the material balance then looks like this. I want to make sure that you've got this one. R sub I times V. Right, this is the material balance for a batch system. The great advantage of that is A, it's really simple, and B, it can be applied to any number of reactions in the system. The disadvantage is if you have more than one reaction or it's a particularly complicated system, you probably can't solve it by hand. But as you will see on Friday, as you will see in the course of the homeworks and the lectures, MATLAB is particularly useful at solving these things. Since I have hit on MATLAB right now, if you plan on coming to the problem session on Friday, where Jenna's going to go over how to use the ODE template in MATLAB to solve these things, try to bring your computer with MATLAB with you so that you can work along. Otherwise, I don't know. I would assume that it would be more helpful to work along than not. So bring your laptop on Friday if you're going to come to that problem session. So if we look at this rate sub I, that's it, right? Okay, good. Want to make sure I get everything. Rate sub I generally looks like rate of either generation or consumption. It could be either one. Right, we don't worry about the sign of R just yet. Of species I per unit volume. Right, that's why we have this V up here. Rates are typically defined on a per unit volume or per volume element of your reactor. The stoichiometry of the system indicates that there has to be a particular relationship between the rates of disappearance of A and the rates of disappearance of everything else or the appearance of everything else. Right? If I cut A in half, I can end up with 2 of the other elements. I can't end up with 3 of the other elements, or one of each. You'd have 2 pieces. So the stoichiometry of the system indicates that certain relationships hold, such as R of A. So the rate of either generation or consumption of A is typically one of our reactants, so it's usually going away, over the negative of its stoichiometric coefficient is equal to the rate of consumption of B over the negative of its stoichiometric coefficient. Right? And you might have gotten exposed to that a little bit in CENG 100 where we went over stuff like this. All that's saying is the molecules are transitioning back and forth between each other. Stoichiometry says that the rate of generation or consumption of each one has to be proportional. If you want to talk about the rates of generation, so R sub C over little c is equal to R sub component D over the stoichiometric coefficient of D. There's nothing unique about this. Again, it's sort of like saying it's the same kind of stoichiometry we had with the stoichiometric table, right? If something disappears from over here, it's got to show up over here. That's all that this is saying, is those rates have to be related. That is going to be particularly useful when we get to multiple reactions. It's useful on a single reaction, but it's very useful on multiple reactions. But it's only useful in the sense that, oh yeah, I need to take into account stoichiometry. I can't ignore stoichiometry. The reason that rates are typically defined as per unit volume is so that we can do the following. Remember, we said that the moles of something is equal to the concentration of something times the volume, right? We defined it the other way around. We said concentration is moles per volume. We can spin it around this way. If we say something like this, then the rate of change, dNI dt, is equal to C sub I times V, right? And now we can apply the chain rule to something like that. If the volume is constant, which again, in a batch reactor, volume is typically constant, then this volume term can come out to the front of the derivative, and all we're left with is V times the change in concentration with time. So again, this is primarily true for batch. It also holds for liquids in any kind of a system, but most of the time we're going to use this for batch. Because again, batch, you dump it into a stainless steel drum, seal it, and walk away. The volume can't change. If it does, it probably means it blew up or collapsed. So if I take this term, this one, compare that to this term. Right? They're pretty similar, except now I got a volume out front and I've got a concentration. But they're still both going to be equal to R sub I times V. All I did here was change N sub I into a C sub I times V. Then, once I substitute that in there, there's going to be a V on either side of the equation, right? There's one V over here, and there's one V right here. So those V's will cancel out. Again, for a batch system, the volume is constant, so we can do things like that. So the end result, if you substitute that into the previous material balance, is d sub I dt is equal to R sub I. Almost all kinetics in all of chemical reaction engineering are written in a form like this. We always talk about concentrations because that R sub I is almost always dependent on the concentrations rather than the moles of stuff that you have present. This other form over here is really useful, but the only way that you can use this form up here at the top, that material balance, is to evaluate R sub I, and as we'll see in a minute, R sub I always depends on C, so it's usually easier to just come over here. The disadvantage to this form is it only gets that simple if V was constant, and sometimes it's not. But if you're making a measurement in a lab somewhere to try to figure out, for example, what the kinetics of a particular reaction are, then you can sort of fix the system to a constant volume just to make the math easier. But this is usually where we will start. You will be solving this equation a lot in MATLAB or the previous equation a lot in MATLAB. Or you can solve it by hand for certain very simple situations. So drawing from your knowledge of differential equations, there's something else that's missing from that. What is it? I can't solve that yet. What do I need? An initial condition or a boundary condition. Because it's time, we like to call it initial, but boundary is fine. We need somewhere to start, right? If we dump this information into MATLAB, we have to tell MATLAB where to start. If we want to integrate it directly or try to solve that directly, we have to have bounds for our integrals, or we have to know how to evaluate that constant of integration after we integrate everything. So there's always an initial condition, which is simply Ci of whatever you have at time 0, is usually defined as C sub I 0. Right, kind of a generic definition. However much you started with is what you started with. So you always need that initial condition. If you get lucky, or if you get an exam question, you will be able to solve that by hand, right? It'll be a simple integral. They'll all be separable. There's only like 2 or 3 integrals that we can actually solve by hand. I will have a little integral page on the exam, so you don't have to try to remember, oh, it was, what's the integral of 1 over 1 minus c, or something like that. I will have the general template for those integrals, the indefinite integrals, that you can use. You should nevertheless know some of the simple ones to get things like exponentials and logs and that sort of stuff. In order to make any progress on that, we need some way to figure out what the form is for r sub I. Right, this is still an unknown. We're going to spend a fair amount of time, actually, let's see, next lecture and then almost all of the week after, figuring out how do we come up with equations or expressions for r. The simplest expressions for r are the ones that you probably got a little bit of exposure to in CENG 100. The simplest expressions are for what are called elementary reactions. So an elementary reaction, if we take the general form A plus B goes to C plus D. First, that is an irreversible reaction because I drew the arrow going in one direction. Next week, we will spend all week dealing with reversible reactions. But what an elementary reaction says is the rate of reaction is proportional to the concentration of the reactants, raised to their stoichiometric coefficient, which is kind of a mouthful, and if you've never written it before, the general form looks kind of nasty. So the rate of disappearance, which, yes, by convention, we always put that R in the middle, or out ahead of it. The rate of disappearance of species A is equal to some proportionality factor K times the product of the concentrations raised to their stoichiometric coefficients. I get to mix. When I say product, I mean like the multiplicative product, not the product as in they are species products, and yet it is the product of the reactants. So that looks weird. That is the general form that I would have given you at the beginning of class. And the reason we generally have to write this form in its sort of odd-looking math form is because until we know what the reaction is, we can't write down a rate. Once you have the rate, it almost becomes second nature to write down an elementary rate law. So for the reaction that we have up here, this would look like K times C sub A raised to the stoichiometric coefficient A and B raised to its stoichiometric coefficient B. Right? But the only way that I can go from this step over here to this step over here is if the reaction is known. So this is the general form, which is why I gave you the general form. I have to admit, it's not very often that I write down the general form because elementary reactions, once you look at the reaction, it becomes pretty straightforward to write down what the elementary reaction rate is because it's the product of the concentrations of those species raised to their stoichiometric coefficients. If you had other reactions, so I'll write a couple more over here. If you just had something like A goes to B, then you would have minus R sub A is equal to K C sub A raised to the A. Right, there's only one reactant in that system, so it's just C sub A times A. This form that I wrote over here is almost the only one that you can solve by hand. There are a few examples of that form that I have down there on the bottom that you can solve by hand. There's not very many. Most of the time it involves making an approximation. Like if I dump in just a lot, I was going to use a different word for a lot of B inside there, then the concentration of B is approximately constant and you drop that other term. But most of the time we're stuck, if we want to solve it by hand, i.e. if I want to write an exam problem, it'll probably look like this because that's about the only one that we can integrate. If you do anything else, you start to get into coupled differential equations, and it's very easy to put those on homeworks because you have MATLAB. It's very difficult to put those on exams because you don't have MATLAB. So this is a very common form as well. Yeah?
So for this example right here, would we still make the coefficient of species A 1, or do we leave it as it is?
Most of the time you should set it to 1.
Okay.
Yeah.
And that doesn't affect the rate at all?
Well, if you carefully follow that, if you either do that algebra initially and then write everything afterwards, having set A equal to 1, you'll be fine. Or if you leave it as A is not 1, just be careful that you keep that assumption all the way through. You will end up with the same sort of final answer, right? You can't change the kinetics of the system by changing the way you write it, but some of the numbers might look different along the way. Normally, we would set A is equal to 1 such that this looks pretty simple, and it just looks like K times CA. Yeah?
So since we're dealing with the reactants, would the nu be negative?
Which nu?
The nu subscript I, the stoichiometric coefficient?
No, they end up staying positive. I guess if you wanted to put an absolute value on there, that's a good point. Now this is going to look really compact. It's always, it doesn't invert like that. That's a good point, though. So these forms typically get coupled with, if I look at any C sub A, take that C sub A, how do I get an expression for C sub A? We have an expression for that, which is over here in the middle. Right, so I would plug that equation into one of those rate laws, and you can see pretty quickly the rate laws can get kind of nasty, which is another reason why we use MATLAB to solve so many of these, because it can be quite helpful. If we take a simple example, I've got about 3 minutes, so we can work through one of these examples. If we're going to take C4H10 and strip off some of the hydrogen, this is called dehydrogenation. And we'll have phi is constant in a batch system. Oh, yes. What, you've never seen an atomic reaction before? Thank you. If we do something like this, we would end up usually calling, I tend to write things like this just because it's easy. So the rate of disappearance of A, if this is an elementary reaction, is just K times Ca. Right, and then our mole balance is dCA dt is equal to R sub A, which is minus K times Ca. Be careful with your signs. It's usually I will look at a mole balance and try to figure out, should that be getting bigger or smaller? And since A is a reactant, it should be getting smaller, so it should have a negative sign in front of it. Subject to the initial condition that Ca of 0 is equal to Ca0. You could take that and dump it into MATLAB. That is also a separable differential equation, so I can move the Ca over to the other side and get something like the integral of dCa over Ca is equal to minus K dt. I'd have to integrate that as well. This is about as difficult as we can get by hand. Maybe it'll be like 1 minus Ca or over Ca squared or over Ca cubed. Those are the kinds that you should be familiar with from that, what quarters of calculus that you've been taking to integrate those sorts of things. If they get beyond that, we typically dump them into MATLAB. If you figure out an equation like that on the exam and I've asked you to solve it and get a number, it probably means you made a mistake. If it's this massive unwieldy polynomial with exponentials and stuff in it, you probably just made a math mistake. So if you want to brush up on your integration and applying your boundary conditions, this ends up looking like Ca is equal to Ca naught times the exponential of minus K times T. Very common exponential decline. And then you would have to solve the other rate laws, or sorry, the other material balances for the other species in about the same way now that you know what C sub A is. So you'll get to practice that on the homework quite a bit. That should be enough. Almost all the first homework problems or something like that. There's no MATLAB in the first homework. So you should be able to solve everything by hand if needed. Please remember to check your units because K varies. As we'll see tomorrow, the units on K are not constant. They change. All right, thank you all very much. I'll see you on Friday.